In the last video, we have spent a significant amount of our energies and time talking about how numbers are represented in the computer. We talked about binary representation, right? We also talked about how can we represent negative numbers using two's complement. That is, how to represent signed and unsigned integers that we require in our programming problems. We also learned how to calculate the ranges of values, and we saw some of the major advantages of the two's complement, right? In this video, we will talk about some limitations, or what we may call surprises that the two's complement might throw at us, okay? The question you might ask is that as programmers, why do we even need to know about the disadvantages of the two's complement when computer sees these binary numbers? And even before that, you might ask, would I as a programmer need to care about binary numbers when I can write numbers in the decimal system even in my programs? So this video answers these questions. Because as long as everything goes well, you are okay. But what if you don't know the limitations of your machine? The limitations of what we can do and what we cannot, and how to avoid specific weird mistakes and corner cases. Then we really need to understand how the computer represents the positive and negative numbers so that we are not surprised by unhappy incidents. And it is important not only to avoid them, but also understand why they might occur so that we are able to avoid them. In this video, we will discuss overflow and underflow and some typecasting surprises that two's complement has at store for us. But before that, let me just revisit the two's complement with a different definition. So given a bit sequence of a positive integer, the required negative bit representation would be a bit pattern that sums to 0 when added to the original positive integer, ignoring the carry out bit. And this perfectly turns out to be bitwise complement plus 1, as we saw before. Let us say we have this 8-bit integer value, which is the original value that represents 1, and we need to figure out what should be added to this pattern that would give us the result 0, and of course that would be its negative. So we want whichever bit pattern or bit string that gives us the right result, that is 0, okay? And that turns out to be this bit pattern. So this is how we represent a -1 in two's complement. Let's have a short quiz to verify it. So these are two additions. The one on the left is a 2, and we want to find the bit pattern that would give us a result 0 when the carry is ignored. And similarly, on the right, we have a bit pattern that is 3, and we want to find the pattern that represents -3. Yeah? So pause this video here for a moment and solve it by yourself. So these are the two's complement bit pattern representation for -2 and -3 on the right side. Okay, and this is our favorite numbers wheel, where we have talked about the light green inner ring that represents the sign and magnitude encoding scheme, where we saw the disadvantage of having 2 zeros highlighted in yellow. Then we talked about the two's complement representation scheme, that is the darker outer ring. Then we talked about the advantages of the two's complement. And if we flatten this circle, this is the flat version of our unsigned and signed values for a 4-bit representation. And to have a clearer view, here on the right, we have the full range of all the possible values for the unsigned representation. It goes from 0 to Umax, that is the unsigned maximum. And in our particular case of 4-bit number on the left, the range goes from 0 to 15. Whereas this range shifts halfway to make room for the negative numbers in the two's complement, so that the larger values of the unsigned representation now represent negative values, and our range for positive numbers have reduced by half. Okay, in the 4-bit case, the range is 0 to 7 now, and instead of 8, as in the unsigned case, we have -8. That is the 2's complement minimum and goes until -1. These are the legends used. So the takeaway here is that in the unsigned values, as we are going in the direction from smaller to larger values, the smaller numbers can just move straight across to 2's complement notation. But the large positive numbers, the ones that start from the leading one, now get interpreted as a negative number. Okay. Now, what could go wrong with the 2's complement? Well, both the signed and unsigned integers have limits. They have a finite number of patterns, and we could run out of patterns after certain operation. For example, if we add 6 and let's say 2, the result would be 8, and we don't have any pattern using 4 bits to represent 8, and so we could not represent that as a signed number. There's just not enough bits to do that. As can be noticed in the table, there is no pattern that corresponds to the number 8. If they were unsigned numbers, we could, because we have a pattern of 1, 0, 0, 0 for representing 8. Similarly, if we add unsigned 15 and 1, it yields 16. And that would not fit into any of our representations, signed or unsigned. Okay. This is what is called overflow. We can also have a number that is too small to represent. For example, -6 minus 3 would yield the signed number -9. And if you notice, there is no pattern for -9. We only get up to -8. And then if we had unsigned numbers and we subtract 2 from 0, we can't represent negative numbers in unsigned format. So we would be in trouble there as well. The result is only correct modular of 2 to the power of the word length, which is 4 bits here. And we will come back to this shortly. So we have to remember which type of number we have in memory. Is it a 2's complement number or is it an unsigned integer? And that's where we get into data types supported by different programming languages. The CPU may only be capable of throwing an exception for overflow on signed values. However, most of the times the CPU won't throw any exception for unsigned case. C and Java, both languages, would not bother checking whether the arithmetic was correct or not. So you have to do an explicit check if you really want to know whether the arithmetic worked out. As we said that we have limited patterns and values to represent in both of the data types, signed and unsigned. And if we are required to represent a number that is larger or smaller than what could be represented, then we say we have an overflow and underflow, respectively. So overflow and underflow happens when we assign a value that is out of range of the declared data type. Okay. So with this definition, let us visualize the overflow and underflow problem using our favorite numbers wheel. So let's consider one example of overflow and underflow each in the unsigned number case. Here is our example of addition, where we want to add a value of 15, the maximum of a 4-bit number. So we add, so if we add more to it, let's say we add 2 to it, we get the result 17. But since we cannot represent 17 in a 4-bit number and we drop the carry bit in the addition operation, the result wraps around. That is a modulo 2 to the power b, which in our case is 16. And hence 17 modulo 16 gives us 1, and the result is 1. Similarly, we know that the lowest possible value in an unsigned 4-bit number is 0. So if we try something like 0 minus 2 in decimal, it should give us the result -2. However, in the unsigned interpretation, it is 14. That is, if we go back 2 steps in the number wheel, from 0, we get 14. So this is exactly the same kind of modulo operation. Hence, the modular arithmetic claim has been verified in both addition and subtraction. Now we look at an example in 2's complement. And we know how the range of positive values shifts halfway to make room for the negative numbers, and therefore the range for positive numbers reduces by half, right? So we have -1, and we add it to the value of 2, and this is what we get in binary form. So we move clockwise on the numbers wheel as we are adding a value, and that gives us the result of 1. And similarly, 6 plus 3 gives us 9, but because the maximum value that we can represent in 4-bit 2's complement is 7, and anything above that get wrapped around, right? And we get -7. So this is how overflow and underflow occurs. Now let's turn to another surprise that the 2's complement has at store for us. These are some of the values to remember, and we have seen this slide in our 2's complement video. Just to recap on these values, when we are thinking about integers, as for unsigned values, we have a special value called umin, which is the smallest number we can represent, that's 0, the bit pattern of all zeros. And the maximum is umax, is the unsigned max, which is all ones, obviously. And that would correspond to the 2 to the power w minus 1. While in 2's complement, the tmin is 2's complement minimum, is the biggest negative number we can have, which would be the pattern of 1 followed by all zeros. And then the tmax is a 0 followed by all ones. So the maximum number is only half as big as it was for the unsigned values. And the negative 1 is represented by the sequence of all ones. Let's look into some programming aspects of signed and unsigned representation in C programming language. So in C, we use the character U to represent an unsigned constant. The constants by default are considered to be signed integers, and you need the U character to represent it otherwise. Okay. In this slide, we will talk about casting. Casting is when we want to change or convert between different data types. In this case, signed and unsigned. So here we look at some casting surprises that might put us in hot waters if we don't understand them. So this is how you define your variables of integer type. By default, int would be signed unless we use the keyword unsigned for declaring an unsigned integer. Okay, and the casting from signed to unsigned and vice versa might be performed by the compiler in 2 possible ways. Explicitly, you would have to use the C construct for casting. So the int inside the round brackets changes the type of variable ux from unsigned into signed. And similarly, in the next statement, we want to convert a signed integer into unsigned integer, okay? But if you don't mention it explicitly, the compiler is going to perform it anyways. The compiler would implicitly go on to do the conversion with some form of warnings. So the 2 important questions: how does casting between signed and unsigned work, and what values are going to be produced? Well, the bits are unchanged. They remain unchanged. They are just interpreted differently, as we know, right? Here is another casting surprise that the compiler might throw at us while evaluating an expression in a conditional statement. If you mix on signed and unsigned integers in a single expression, the signed values are implicitly cast to unsigned. So unsigned dominates, and we need to be careful about that. In which case, our smaller numbers would be interpreted as larger numbers. Right? Let's look at what happens here in some examples. Suppose that we have 2 constants and we want to see how the compiler interprets these expressions. In the first instance, we have the constant 1, that is 0, and the constant 2, that is 0 unsigned. Both of these values are same, but the compiler interprets them as unsigned. But since 0 in signed and unsigned would be the same, the relation evaluates to equal. However, the signed value is reinterpreted as an unsigned number. But fortunately, 0 would be equal in either case. So that is pretty easy one. Let's look at the next one, -1 signed and 0 signed. Well, in this case, both are signed, so the compiler does the normal evaluation, and we would expect -1 would be interpreted as less than 0 in terms of bit pattern. Remember that the -1 is all ones and 0 are all zeros, but it is going to be interpreted as a signed value, so that the leading bit or the most significant bit would get the high negative weight, right? Now it would be really interesting if we instead compare the -1 with an unsigned 0. Now the compiler will reinterpret the -1 as an unsigned value. Well, all ones reinterpreted as an unsigned value is a huge number, because we lost that negative weight of the most significant bit. So now we have got a large number, and it is going out to be larger than. So look at that. Just because we have interpreted one of the constants as an unsigned, we have a completely different result, even though we might have been thinking that we are comparing the same values. But that just because how the numbers being interpreted. This is because C has that convention of interpreting everything to unsigned if we would mix signed and unsigned inside a condition expression evaluation statement. Okay, I hope that was clear. So I recommend you to stop the video here for a short while and solve the rest of the examples by yourself to make sure that you get yourself prepared for the casting surprises that the compiler might throw at you. And here goes the rest of the solution. So that is it for this session. That was all you needed to know about signed and unsigned representation in the 2's complement, along with the kind of surprises that we must be prepared in our programming problems. I hope you enjoyed the video. Tech Instance has more for you at store, so I encourage you all to subscribe this channel, and don't forget to hit the bell icon to receive important notifications. And if you have any questions, feel free to comment in the comment section below. Thank you.